Hello everyone, welcome to A plus BI. This channel is all about complex numbers, and in this video we're going to be solving a very nice equation with complex numbers. Is this for real? Let's find out. Now we have z to the power I equals negative 1 to the power square root of 2. Such a weird power of negative 1, don't you think? Negative 1 when raised to the even powers like 2, 4, 6, 8, you get positive 1. If you raise it to an odd power, you get negative 1. If you raise it to the power 0, you get 1. What happens if you raise it to an irrational power? Not even something like a fraction or rational number like 2/3, because that one has a meaning too, right? Kind of like a radical. But we're talking about complex numbers here, so it's a different story. We have z to the power I equals a number. Obviously, the right-hand side is a constant, right? So we're going to try to simplify that. But at the same time, we have a complex number z. By the way, if you're new to complex numbers, go ahead and check out my lecture videos where I go over basics and ask a lot of questions. I also have another channel that focuses on algebra, number theory, and trigonometry. That's called Cybermath. And I also have a shorts channel, which I publish once a week, but still good. Great. Now, how do we simplify this? Thanks to Euler, we have what is called the polar form. So any complex number can be written as exponentials, right? And this one also can be written as exponentials. What's the rule? Z to the power W can be written as e to the power W ln z. And we'll talk about what ln means in this case. Of course, we're talking about the complex logarithm, right? And we can do the same thing on the right-hand side, but the Euler's polar form actually allows us to express negative 1 as e to the power I times theta. To find theta, we need to use the polar form or just plot it in the complex plane, which is basically a fancy name for the coordinate axes, right? But we call it a real axis and the imaginary axis. And because negative 1 appears here, 1 unit away from 0, and it's on the other side of the real axis, so it makes an angle of pi radians. That's why our theta in this case is going to be pi. The modulus r, which you can write here, is going to be 1 because it's distance from 0. So negative 1 basically can be written as e to the power I pi, right? But that's one of the values of negative 1. What does that mean? This is kind of like multi-valued. In other words, we can express in the complex world negative 1 in infinitely many ways. To count for those, we're going to go ahead and add 2 pi n, which are multiples of 2 pi. So negative 1 in the most general sense can be expressed like this as an exponential, as a complex or imaginary number. Great. So that is negative 1, and we're going to raise it to the power root 2. That's going to be fairly easy. What about z to the I? We're going to use the formula for that, right? Z to the I from the formula can be written as e to the power I ln z. And since we don't know what z is, ln z is unknown either, right? Or it's not known either, I should say. So let's go ahead and set these equal to each other. E to the power I ln z equals, what do we have on the right-hand side? Negative 1, which is e to the power I times pi plus 2 pi n. And then you have to raise it to the power root 2. Everything is simplified to the exponential level. And this is amazing, don't you think? We have now everything is exponential form. We're going to go ahead and distribute. This gives us e to the power I ln z equals e to the power I root 2 multiplied by pi plus 2 pi n. Now, if you want to keep things a little simple, you can assume that, okay, suppose n is equal to 0, then we're going to get the principal value, which is obviously something that usually agrees with real numbers, right? Because a complex number has 2 square roots, but one of them is considered the principal square root. By the way, I forgot to tell you, I squared is equal to negative 1 because I is the square root of negative 1. I say the square root because it's considered the principal square root of negative 1. Okay? In other words, there are 2 numbers whose square equals negative 1. Those numbers are I and negative I. And obviously, square roots of a complex number are opposites. Their sum is 0, so that when squared, they give you the same number. And you can find it for any number. The only exception is 0 has a single square root, which is itself, right? Great. So if n is equal to 0, we get something like this. E to the power I ln z equals e to the power I root 2 times pi. Now, in this case, are we allowed to get rid of the I? Absolutely, because I doesn't equal 0. From here, we get ln z equals root 2 pi, which is fairly interesting, right? And from here you get z equals e to the power root 2 pi. But are those the only solutions in this case? Of course, we're talking about n equals 0, a particular case. Let's go ahead and look at the general case and see if we can solve this problem in the most general sense, okay? Let's go ahead and erase this area now so we can use it again, being lazy here. All right, now we're going to go ahead and do this. Natural log both sides, and it's going to give us the exact same thing. I ln z equals I root 2 multiplied by pi plus 2 pi n. And then here you can cancel out the i's, and you end up with ln z, which means since we know that z is equal to e to the ln z, even for complex numbers, right? And you can definitely check this out. By the way, ln z can be expressed, again, that's multi-valued and can be expressed in infinitely many ways. For example, if z is equal to r times e to the I theta, from here ln z can be written as ln r plus I theta. By the way, r here, ln r is a real valued logarithm, but this is the complex logarithm. Some people will just use log, but then log and ln, it's kind of confusing, don't you think? Just think of this as the complex logarithm, okay? And you'll be fine most of the time. And in this case, where we are allowed to add multiples of 2 pi to it, because theta basically just represents the principal value or the principal argument, okay? Now, let's go ahead and use this formula here. Z is going to be then e to the power root 2 multiplied by pi plus 2 pi n. Wait a minute. I thought this channel was all about complex numbers. Why did we get a real answer? Well, it's possible that you may get a real answer because real numbers are also complex numbers, which means the set of complex numbers contain real numbers. Why? Let me tell you real quick. For example, in the standard form, you can express a complex number as a plus bi. And if b is equal to 0, of course, a and b are real numbers in this case, right? If b is 0, then you just get a, which is a real number. So absolutely every real number is a complex number, but not vice versa, obviously, right? There are numbers that are like 3 plus 4i, that is complex, but they are not real. And there are some numbers like 2i that are imaginary because they don't have a real part, and definitely they're not real either, okay? Great, so that kind of seems to give us the solution, doesn't it? So this we should be able to take as a solution. And again, if n is equal to 0 in this case, you will find the exact same solution that we found before. Where is it? I lost it. Anyway, I think I erased it. But you get the idea, right? So this should be the general form. So what is really cool about this problem is that the answer is real, for reals. And this brings us to the end of this video. Thanks for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time in another video. Until then, be safe, take care, and don't forget to check out Cyber Math and aplusbi, and bye-bye.